Good morning, everybody, and welcome to this parallel session on the EU Hydrogen Research Days, a session that deals with sustainability and supply chain of hydrogen technologies. My name is Claudiu Pavel. I'm one of the project officer at the Clean Hydrogen Partnership, and I'm going to be the moderator of this session for the next 1 hour and a half. Let me give you some words about what this session is going to be about. First of all, we learned yesterday from many speakers, including the European Commission, about the need to support hydrogen technologies becoming more sustainable, more competitive, and as well to enhance the circularity, for example, by the reuse of the components. It's important to limit as well the waste production and recycling some key materials. Therefore, in this session, we're going to dig even further into some achievement and challenges of few projects dealing with recycling from one side, life cycle assessment from the other side, but as well, we'll present you some preliminary results of an important study on hydrogen supply chain. And in the end, we'll introduce an important initiative launched on behalf of the Clean Hydrogen Partnership, such as a sustainability panel. This will be implemented, set up, and managed by some consulting companies. Before starting, I would like to remind the audience to drop the questions in the slide box by selecting the right room related to this session, and if possible, to direct the questions to a specific speakers. In the end, we plan to have a Q&A session to pick up some of these questions and to address them with the speakers. Let's get started. I'm inviting first Ilaria Schiavi. She's project manager at Environmental Park to present the results of Best for High project, a project that stands, the acronym for Sustainable Solution for Recycling of End-of-Life Hydrogen Production, a project that has as scope to develop and validate novel recycling processes for PEM and solid oxide fuel cells up to TRL 5. Ilaria, the floor is yours. Looking forward to get some more insights from your projects. Thank you.
Thank you. Thank you very much, and good morning, everyone. Thank you for the introduction. So today I'm going to present the results of Best for High. Best for High project started in 2021. It was awarded a grant under the call topic that you see on the left, so on development and validation of existing and novel recycling technologies for key fuel cell and hydrogen products. The project is about to finish. We can say they were about 90% of the implementation at the beginning of this month. Effectively, we only have 2 months left. Our total project budget was just over 1.5 million. This is a research and innovation action, so it was fully funded by the Clean Hydrogen Partnership, which we thank for the funding. Just a few words about the consortium. Environment Park is a scientific and technology park in Turin, is also a business support organization, and indeed we work on hydrogen technologies. We represent the local supply chain on hydrogen. We work together with 3 research centers, the Politecnico of Turin, which looked after the solid oxide fuel cells aspect, the CEA from France, who looked after the proton exchange membrane fuel cell, and the University of Ljubljana, which studied the life cycle aspects of this study. We also had on board RINA, again working on standardization and other support to the business aspect of the project. Then most importantly, we had a good representation of industry, and this helped a lot in our project. So we had a recycling expert, Hensel Recycling from Germany, and his third part, Idolab. We also had two companies supplying to us the fuel cells and also helping us in the final phase of the project. So we had EKPO from Germany for the PEM fuel cell and Elcogen from Eastern Europe for the solid oxide fuel cell. So this is a representation of our project concept, and you see circle already gives you an idea of what our main objective was. So yes, developing some technologies for recovering precious and critical and rare material from fuel cells, but also trying to put them back into the manufacturing of the same fuel cells to evaluate how they could perform with these secondary raw materials. So the target technologies already said proton exchange membrane fuel cell and solid oxide fuel cell. We looked to the end of life of these technologies. We tried, first of all, to understand how we could disassemble and we could dismantle them so that the further steps for the recovery of the materials could be more successful and have a higher yield. And we developed some initial thought about how we could even mechanize some of these dismantling procedure, and we experimented also a procedure which gives us a very clean CCM and also allows us to recover the membrane. Our processes, which is the core of the project, we had the brief to try and adapt to existing technologies, and then to try and develop some new technologies for the recovery of platinum and ionomer from the proton exchange membrane fuel cell, and nickel and the yttria stabilized zirconia from the solid oxide fuel cell. We managed to develop these four technologies, and also up to TRL5. And also we studied how to recover lanthanum and cobalt from the cathode part of the solid oxide fuel cell up to TRL3. Our focus was to try and find low impact technologies. So technologies which use mild conditions, they use perhaps mild chemicals, low temperature, and that allows to recover not just platinum, as it happens with pyrometallurgy, but also other components of the cells. These materials that we recovered, they were recovered in a form which is a typical precursor form for then going on to manufacture the new fuel cells. So we managed to develop and assess the manufacturing methods with these precursors recovered from the end-of-life materials. And then we studied the performance of these cells with this recovered material against the performance of the cells with 100% virgin material. Alongside this technical circle, there is also a lot of work gone onto some conditions, some aspects which support the opportunity for recycling of this technology. So we looked into the regulation aspect, how this recycling could be policed, and also the reuse of the material could be policed. We tried to understand if there is anything in the standards that could support this virtual circle. We are also working on some training modules to offer an operational understanding of the technologies that we developed. We looked at how the new business opportunities could be developed by these processes, and also we looked into the LCA and LCC analysis of these aspects. The state of the art is that there isn't much out there in terms of regulations. The Critical Raw Materials Act was issued only in March this year, so hopefully and clearly things are moving in this respect. Standards are also lacking. For the LCA and the LCC, owing also to some previous projects such as high-tech cycling and also some sister projects that you will see later later on. There are some data, but they are very limited. There is basically no information on the end-of-life aspects of these fuel cells, and sometimes there are not even available inventories for some of the technologies that we studied. Also, the supply chain is quite interesting. It needs to be developed and is still under debate what could be the best supply chain for this kind of recovery and recycling process. Here are some of the key outcomes. Clearly, being now towards the end of the project, many of the targets that we had have to be achieved. And luckily for us, we managed also to get a bit further on. So we had as a target to recover at least 80% of the platinum, and we managed to achieve up to 85%. We needed to, at least from the hydrometallurgical process, this is the process that we adapted for recovering platinum from PEM fuel cell at end of life. Then with the novel processes, we wanted to try and achieve at least 90%. And with the alcohol dissolution process and the electroleaching and electrodeposition process, we managed to achieve up to 95%. We actually studied also the recovery of ionomer. We were successful in recovering the ionomer. However, this is a very challenging aspect of the recovery for our technologies, and I'll explain a bit later. For sure, we managed to recover ionomer in solution, and we managed to recover 100% of the membrane. We also wanted to use at least 90% of the recovered platinum into the manufacturing of the new membrane electrical assemblies, and we managed to achieve 100%. So we managed to find a way to manufacture these MEAs, which could use this recovered platinum without any issue. In the process, our colleagues managed to apply for 2 patents for these new technologies that we have developed, and I think that this is a very interesting achievement for these kind of projects. For the solid oxide fuel cells, our target was to recover at least 80% of the incoming material, combining together hydrothermal and hydrometallurgical processes, and we managed to do that, so to recover both nickel oxide and yttria-stabilized zirconia. We also wanted to explore the recovery of lanthanum and cobalt from the cathode part, and this we managed to achieve again 80%. We also managed to use these materials up to 30% into the manufacture of the new fuel cells, and this has been achieved. So the manufacturing process could be successfully adapted to accommodate for the different particle distribution of the materials that we recovered, and actually our colleague from Elcogen managed to produce new cells. What's happening now? Now we are in the process of actually evaluating the performance of these cells that we have manufactured with the recovered materials. We have already done some performance measurements in the lab, obtaining very good and very encouraging results. We are in the process now to use these same membranes into a stack, which is being a kind of industrial stack, which is being tested on a industrial test bench according to industrial standard. So we managed to finish the test, and we are now looking into the data to confirm the good performance that we achieved in the lab. At the same time, we are working on the solid oxide fuel cell. All what I said above was for the proton exchange membrane fuel cell. We're also exploring some open loop recycling options, because clearly some of the material might not be able to be used again into solid oxide fuel cells. For example, we know that for platinum there is a very buoyant market, so that's not so much of an issue. For the materials recovered for solid oxide fuel cells, we are actually exploring how they could go into the synthesis of the NMC materials for batteries, which is clearly a very interesting supply chain also to provide for. Other work in progress, I'd say, is on the LCA and NLCC. So we managed to develop a new innovative life cycle inventory for the recovery of lanthanum and cobalt from solid oxide fuel cell. So at least we have mapped the process, clearly being low TRL processes. The first information that we have might not be the same that could happen from industrialized process, but at least we know what's happening in the process. We also managed to develop the life cycle costing and for the recovery of platinum with the hydrometallurgical process. Also, it helped a lot having on board an expert, a member of the recycling industry, and we managed to see that there are promising results for the recycling industry if it actually goes on to recycling platinum from the fuel cell technologies. This work has had some challenges for sure, but they were somehow inside our project, because we had low TRL processes, but at least we managed to ensure that we could see where are any hotspots, if any, of the technologies that we are developing. And so those are the parts that we need to be more mindful if we want to scale them up, to ensure that we keep a very low impact for these technologies. Also, we found out that there weren't that many data for some of the virgin materials, especially the rare earth elements and some of the critical raw materials. This has been quite a challenge, because clearly if we want to compare the advantage of our processes, we need to have very reliable data also for the virgin materials. However, all this work has been done in cooperation with projects EGHOST and Schiavi, which you will hear from in a little while. And this has been really, really useful to be able to cooperate and work together to obtain some results. We are still working also on the aspects related to the regulation and the standardization aspect. There are a number of directives which are very relevant in our opinion for the managing of the end-of-life hydrogen technologies. They are all under review, and of course with the new critical raw material acts, there is even a stronger push towards trying to see how the recovery of material and perhaps the introduction of recovered materials into new production could be policed. We're also keeping an eye on the batteries. At the same time, we saw that for standards, there isn't much there, but we identified the relevant standardization committees that we could work with to keep on this aspect. And we also thank the Horizon Standard Booster, who we work with to identify these standards. What are the risks, the challenges, and the lessons that we learned from this process, from this project? We actually tried to apply some of our technologies to the recovery of precious material from other fuel cell and hydrogen technologies, namely from electrolyzers. And you can see in the pictures the platinum group material solution that we managed to obtain from the processing of some electrolyzers membrane. So that was successful. We managed to adapt the process to accommodate for these different materials, but actually we found that it was difficult to get hold of these end-of-life materials. So in a next phase, if we want to proceed with this work, for sure, it will be necessary to involve the supply chain. We saw in our project that the involvement of the industry and the supply chain, the recycling partner, for example, it was really fundamental to obtain such good results. For the characterization of the ionomer as well, we're still working. Some specialist expertise needs to be brought in because obviously the ionomer has its challenge. There are different chemistries. It needs to be characterized by experts. And unfortunately, for this reason, we couldn't quite use it in the manufacturing of new MEAs. Our exploitation plan, we identified 13 key exploitable results. We took advantage of the Horizon Result Buster. It was really useful to help work with them. And we explored 3 different types of these key ER. And we are now working with the same methodology for the rest of the key ER. But you know, it's really good. We know that we can bring these results forward into either the industry or for further research. With respect to the impact, clearly you see that the technologies have obtained new and important results. We are aware that these are TRL5 results, so there is still some more to be done to actually get onto the higher scale of TRL and also a higher scale on of the plants. Obviously, materials is still not there, so we still have time to work on it. I guess that one of the major impact of this project, aside from the results, is how we contributed with the life cycle assessment of solid oxide fuel cell and proton exchange membrane fuel cells. So there has been some advance in there. We managed also to map these end-of-life strategies, and so we are prepared with the models which could be used for future assessment. And also we are developing and validating the model for the life cycle costing of this end-of-life technology. This brings me to the end of my presentation. I thank you for the attention, and I pass the floor back to Claudiu. Thank you.
Ilaria, thank you very much for introducing the project results. And I think the Best for High has achieved something very good for all the overall community. And here, I'm not referring to the targets for the platinum recovery in the manufacturing, putting platinum back in the MEA, testing and characterizing these new materials. And very glad to see that in the other project even reach not only the targets, but even better results. And here I'm referring for the platinum as well, for the CRM in the solid oxide fuel cell. I believe this is a great achievement, and it's not only based on luck. I think it has been a lot of hard work in the consortium. I know that the partners really are engaged in getting these very good results. Allow me to break the rules on the question, because I have one on top of my head that I would like just to go with you. I think the time is still allowing us. I was wondering, related to the recovery process, in particular on the alcohol dissolution, electroleaching, developing in the project, how this process of recovery can be applicable for the recovery, for instance, of iridium from end-of-life water PEM electrolyzers. Is it a straightforward process? It involves some further research effort for that? Maybe you can answer to that, please.
Yes, yes, for sure. The membranes that come in are much different. So we learned that, for example, there is no opportunity to put in a solution the whole of the membrane. So that needs to be worked about. Then we actually managed to find through the alcohol dissolution process in that solution, the yellow solution that I showed, the iridium and the platinum. The iridium is clearly much less than the platinum. We are talking about 10 times less than the platinum. So the further process is how to extract successfully the iridium from the platinum, from the solution, sorry. Because clearly these are materials which are very stable, and how to capture them, that's where we need to work to actually ensure that we can precipitate them properly without perhaps using too much harsh conditions, but trying to do it again in a mild condition. So the challenge is really there. And also, as I said, is actually obtaining end-of-life materials, because that was quite difficult as well. We had very few samples that we could use, and we were lucky that some of our colleagues had this material, and also by chance our recycler was invited to dismantle some electrolyzers, but clearly there is a need to understand if this material is available, where it is, and how we can actually get hold of it.
Yeah, excellent. Thank you, Ilaria, once again. And thank you for somehow bringing to the next speaker. And you make the link now with Schiavi and EGHOST project. This is a good opportunity for me to introduce Javier Dufour, Head of Energy System Analysis Unit Institute at IMDEA Energía. Javier will actually present two projects, SH2E, or Schiavi in short, and EGHOST. Two projects that are linked to each other. They both are dealing with assessment development of guidelines for life cycle sustainability, with two specific applications for PEM, fuel cell, and solid oxide electrolyzers. Inviting Javier to start first with the Schiavi project, which is the acronym for Sustainability Assessment of Harmonized Hydrogen Energy System Guidelines for Life Cycle Sustainability Assessment and Prospective Benchmarking. Javier, the floor is yours. Looking forward for your presentation. Thank you.
Thank you, Claudiu. So let me begin just first thanking to the Javier Partnership for inviting us to present our two projects, the S.p.A and the EGHOST. And coming first with the S.p.A project, you can see here, let me say, the administrative information of this project. This project began in 2021 and we will finish by the end of June of the next year. So that means that we are more or less with an 85% of the implementation of the total project. You have there also the total budget and the contribution of the Clean Hydrogen Partnership. You can see that there are other essential contributions coming from our Japanese partners, is the Institute for Applied Energy. But you can see more information about the partnership and also the scope of the project in the video. Then if you can launch the video, please.
The climate emergency has driven multiple lines of research and energy policy, leading to unprecedented advances in renewable energy technologies, clean mobility and hydrogen, among other fields. Hydrogen appears as a great opportunity due to its flexibility and versatility as an energy vector, allowing different primary energy sources to be linked to different sectors. Hydrogen can store the energy produced by renewable sources, transport the resource to places where demand is greater, and to use the energy in applications such as transport or the production of chemical products and alternative fuels. As a result, the environmental, economic, and social impacts of renewable energy solutions are changing. For example, the complexity of the supply chain and the dependence on new mineral resources are some of the challenges that need to be addressed. This leads to the need to properly assess the sustainability of different energy solutions, in particular hydrogen systems, both at present and in the medium to long term. From an environmental point of view, the carbon footprint is the most common indicator. However, there are others such as acidification, eutrophication, and depletion of mineral resources, which must be analysed taking into account the entire hydrogen life cycle and not only its production phase. In this sense, life cycle assessment is an established methodology for assessing the potential environmental impacts of a product system. Together with a coherent analysis of the costs and social risks involved throughout its life cycle, this results in a life cycle sustainability assessment. To this purpose, the European SH2E project, funded by the Fuel Cells and Hydrogen 2 joint undertaking, serves as a catalyst for the development of well-defined guidelines and tools for the sustainability assessment of hydrogen systems. The results of their SH2E project will contribute to the correct deployment and implementation of sustainable hydrogen systems, making the life cycle sustainability assessment of these systems accessible to a wider public. To this end, the SH2E project relies on the participation of internationally renowned institutions in the fields of energy, hydrogen, and life cycle management. IMDEA Energy and Aragon Hydrogen Foundation in Spain, Green Delta and Fortune Zenitum Jurek in Germany, CEA and Symbio in France, and the Institute of Applied Energy in Japan. If you want to know more, please visit www.sh2e.eu.
So that was the video, and then you now can have a general idea of our approach to this project. If we go to just to the slide, the final aim of this project is just to provide a very well-defined, validated, and practical framework to perform life cycle sustainability assessment in our field, in the fuel cells and hydrogen field. And this will be supported also with an open access tool I will present later, a bit later. The final aim with these new guidelines is to support a robust decision-making in all the matters, all the issues concerning fuel cells and hydrogen, just also attracting this, or just introducing the sustainability criteria to this decision-making. And also these guidelines and the web tool can be used to benchmark our systems with competing technologies. So to reach this overall objective, we have also developed specific guidelines for the environmental life cycle assessment, life cycle costing, and social life cycle assessment. Actually, you see here, this is the need that we are addressing in the SEA project. For the environmental part, we have updated all the LCA guidelines that were published, that were available previously, that come from the High project, also from the International Energy Agency Hydrogen Task 36. And also, of course, we have integrated, or we have taken into account all the activities of the ISO standards. Then a novelty in our project is that we have also developed and we're implementing a new criticality indicator for in this life cycle assessment. And also, since several of the hydrogen technologies are at low TRL, TRL 5, 6, we have developed also a prospective approach to complete this environmental life cycle assessment. Coming to the life cycle costing, we have selected and we have defined the most adequate indicators for the hydrogen field. And we are also using this prospective approach based in different KPIs or learning curves. In the social part, I can say that the hydrogen is a kind of a pioneer in this social life cycle life cycle analysis. I think that our sector will be the first with these available guidelines to perform the social life cycle studies. And just now we are integrating the previous guidelines in one overall life cycle assessment in a harmonized way. We are avoiding this possible double counting of different impacts in different categories, in climate change or in acidification or costing and so on. And then right now we have completed the guidelines for the environmental life cycle assessment. Also, we have this new criticality indicator that is being integrated in the tool that I will show in the next slide. We have also completed the life cycle costing guideline and the social life cycle assessment guidelines. And right now we are integrating all of them, all this information in these life cycle assessment guidelines that will be issued by the end of the year, just along the next month. These new guidelines will be ready. And as I have been commenting, all these guidelines will be supported by a software tool that will be in open access, so it will be available for all of you. Here you can see some screenshots of this tool. Right now, we have completed the environmental part of this tool, and we are now integrating the economic and the social part. Just you can see in this first screenshot, you can choose if this is a mature technology or is early stage technology. Then we need to use this perspective approach. So we have here, or behind this, we have some inventories for this perspective approach. We can also select the boundaries of our system. Is just for hydrogen production, or the include hydrogen use, or the storage is involved also in this. Then this is also a novelty because, as Ilaria has explained it before, there are few information. There is not much information available about the end of line, and actually we have a very good collaboration with Belfort High project because we are exchanging this information with the inventory for end of life, and we are just giving them this new methodologies or new guidelines for completing life cycle assessment, life cycle costing to the end. And so we are exchanging this information. We are just checking the information between these two projects. But this is a good novelty also of our guidelines, that ethanol life is there and it was not in previous methodology. So we have different approach for this end of life. We can just use the formula for circular from printing. We have the cycling approach with inventories coming from technical partners or from Belfort High in this case, or kind of projects. We can use other projects, and then we can just select a template to integrate all this information, and then we will obtain three, let me say three with this aspect. This is just for the production of hydrogen. And then once you have these three, you can upload the information you have, or you can just use available inventories in different databases. So we have been testing this methodology with two case studies. The first one is just for hydrogen production, and in this case we are just approaching low TRL technology. It's electrolysis. Electrolysis, you know, this is a TRL 5-6 more or less, and then just to have the complete system, we have coupled this solid oxide electrolyzer with a concentrated solar power plant. And then you can see here the benchmarking with other different hydrogen technologies. Actually, this steam methane reforming was our benchmarking technology, and you can see how in this case, the CSP coupled to solid electrolyzer performs much better in this harmonized cathode footprint. But with our guidelines and also with our tool, we can have all information. This is, for instance, the cost distribution for this technology. You can see here the contribution of the CSP plan, of the solid electrolysis part of our plan, and also the very high contribution in this case of salaries, because we need a high number of workers just for the CSP maintenance. Then this increases the total cost of the overall system. And you have here other example. In this case, for the second case study, this is the hydrogen used in a proton chain membrane fuel cell for electric cars. And then the tree is more complete because we have here the production and the manufacturing, production of hydrogen and the manufacturing of the car, and we have here the use and also the end of life. So in this case, we have the cradle to grave approach. And you can see here some results coming from our web tool. This is the contribution of the different systems on the different processes in our system in the different environmental categories. We are using the environmental footprint 3.0 methodology that is recommended by the European Commission. And you can see how, for instance, the hydrogen production is contributing to the different environmental categories. In any case, in my next presentation, you will see more examples of the application of these methodologies and these tools. So, about risks, challenges, and lessons learned, we have not had any major risks. There are no deviations in the project. About the challenge, we are facing, we want to have a widespread use of these guidelines and this web tool. We are hoping that this tool will be a useful tool for all the projects under the Clean Hydrogen Partnership, because we are looking to produce an easy tool to be used. And also these guidelines are also focused in high specialists in life cycle, and this is focused for hydrogen people. So we are facing out several dissemination events. We will have the presentation of these guidelines, the tool, in the next European Hydrogen Energy Conference to be held in Bilbao in next March, in March 2024. And also there will be a summer school, let me say more than summer school, it will be in the spring school that will be held in Spain, in Madrid, in Rey Juan Carlos University. And also we will have a final event in Brussels, just looking to attract stakeholders and all the people interested in these guidelines and this tool. So the next step, we are the final edition of the life cycle sustainability assessment. We are completing also the tool. Then once we have the tool available also with the social and economic part, then we apply it to the case studies. And just next month, we will begin with a third-party review of the guidelines at the tool, just to ensure that these are useful and easy to be used. So coming to exploitation, we hope that these guidelines will be or could be a very good support for the regulation code and standard strategy of the development of the regulation code as a standard. The exploitation plan will come in June 2024, but as you can see, all our developments will be in open access. So our final impact or our final aim is just that you can use all these guidelines and this tool, just a robust framework for a very transparent, harmonized, and up-to-date life cycle studies of the system you are developing. So, and that was all for the C project. So I think I can pass directly to the EGHOST presentation.
Thank you very much, Javier. Yes, indeed, I think we can continue and going straight away with EGHOST and to see how these guidelines are linked later on to the eco-design guidelines for hydrogen system and technologies. If you can upload your presentation and continue your speech.
Just 1 minute because it's uploading them. So can you see now the second presentation?
I think it looks fine. Go ahead.
Okay, so let's go for the second project. This is the EGHOST. This project is, I think, is the first milestone for the eco-design of hydrogen products and hydrogen devices at the European level. This is again the administrative information of the project. The project began also in 2021. It was supposed to finish in December of this year, but it has been extended to 2024, to May to 2024, just to take advantage of the final life cycle sustainability guidelines of the C project, and also with the final information of ethanol light coming from Bedford High. You have also there the total budget and the other financial contribution that again come from our Japanese partner, the Institute for Applied Energy. And again, we can see a video just to frame the total project. So please, you can launch the second video.
The European Commission, citizens and society consider eco-design as a key factor for the compliance of its commitment towards a circular and neutral carbon economy by 2050. Several relevant documents have reflected this commitment, as in the case of the European Green Deal, the New Industrial Strategy of Europe, and the Circular Economy Directive, among others. Eco-design is an effective tool for improving the energy efficiency and sustainability of products and promotes better environmental performance across the value chain of products. The EGHOST project will contribute to positioning fuel cells and hydrogen in this direction and will develop the first preparatory study of a hydrogen product under the principles of the Eco-Design Directive. The project will develop two specific guidelines, one for a PEM fuel cell stack and the second one for a solid oxide electrolyzer. The final goal will be based on three priority objectives. The first objective is based on the development of life cycle thinking tools to assess the sustainability profile of the two selected products, including economic, environmental, and social issues throughout their life cycle, to create a hydrogen-relevant eco-design methodology. The second objective will contribute to European initiatives, creating metrics for prospective environmental and social aspects, giving support to the European hydrogen sector, and setting the basis for future eco-design regulations, according to the Eco-Design Directive. And as final objective, the project will allow the formulation of eco-design guidelines for FCH products, where the lessons learned will be integrated into an EGHOST White Book, a guidance and reference book for any future fuel cells and hydrogen eco-design project. To this end, the EGHOST project relies on the participation of internationally renowned institutions in the fields of energy, hydrogen, life cycle management, and eco-design. If you want to know more, visit us at eghost.eu.
So that was the video. You have seen the overall framework of the projects. So if we go for more specific objectives, as I have commented, the EGHOST project is the first attempt to eco-design fuel cells and hydrogen products, but not just from an environmental point of view, because we integrate also social aspect and economic aspects, of course, to this redesign of this product. So actually, we were just looking at having the first sustainable by design fuel cells and hydrogen products. So with this final aim, we have developed robust eco-design guidelines, in this case for two products, for a fuel cell stack and solid electrolyte stack. As you have seen in my previous presentation, in the C presentation, in this project, in the C project, we addressed the overall system. For instance, for the solid electrolyte, it was coupled to CSP plan. And in this EGHOST project, we are just focused in the two stacks, in the solid oxide stack and the PEM fuel cell stack. You can see here the methodology we have used for this sustainable by design approach. It's mainly based in the typical methodology for design any project, but we have introduced here different sustainability issues. For instance, when we have to define the product or the product system, we have our first sustainability assessment, including environmental, what is typical in eco-design, but also including the social and the economic part. Then we are using the methodology that we were also developing in the C project. So we are very aligned in two projects just to to have the benefits of each of them. A novelty also in this project, as you have seen in the video, is that we have conducted also the first preparatory study of a hydrogen product, a hydrogen device, under the current eco-design directive. You know that a new directive is coming, but we have just completed this preparatory study under the current eco-design directive. And also another novelty or another methodological novelty is that we have used also the prospective approach for the solid oxide electrolyzer stack. So, talking about the main results of our project, we have released 4 product concepts for the previous set redesign. We have 2 realistic product concepts with the new design measure, the new design insights that can be included in the short term or in the medium to long term. Then we have an optimistic product concept that we are just using here the most optimistic results that are now being obtained at the lab scale. And we have also a totally disruptive product concept. In this case, let me say, we are including some very more or less scientific fiction measures. And for instance, just to change the shape of the final stack and so on. And then, okay, I think it's not working now. Okay, now. Okay, that was for the PEM fuel cell stack. And we have also these Ecorys guidelines for the solid oxide electrolyzer stack. In this case, we have just 3 product concepts, the base case study, how the solid electrolyzers are right now. Then we have our realistic product concept that will be in the next for 2030, because in any case, we are using here prospective approach. And then we have also optimistic product concept that will be reached between 2035 and 2040. So we have several initial results here, which is, for instance, the comparison of how some environmental impact are decreased with the new product concepts. You can see here, for instance, that we have just the ionizing radiation during the manufacturing of the solid oxide electrolysis stack is reduced for more than 60%, almost 65%. And also the use of materials is reduced by 70%. In the optimistic case, we are reducing the ionizing radiation for 95%, 96%, and purification is about 81%. So you can see how the new product concepts are decreasing the environmental impacts, but it's also important from the economic point of view. You can see here how the total cost for producing these stacks are reduced with the new product concepts, with the realistic and the optimistic one. And the upper part of this slide, you can see also this factor X is just a benchmarking of the coefficiency of the new product concepts. That means that we are just dividing the coefficiency of the new concept with the efficiency of the base case, and efficiency is obtained just dividing the value, the economic value of the product by the environmental impact. So you have a high efficiency, that means that you are reducing the impact and you're increasing the economic value. So with this new product concept, you can see that we are increasing by a factor of 5 in the case of the realistic product concept, this efficiency, and for the optimistic one, we are just multiplying this efficiency by a factor higher than 11, or almost 11.5. Coming to the social impacts, we are using the methodology I commented in the C project. You can see how we are decreasing the social impact. In this case, for the realistic product concepts, we are just decreasing the impact in forced labor by a matter of 63%, and child labor is at 66%. And if they are furtherly decreased, it will go for the optimistic product concepts. We have a reduction in both cases higher or very close to an 80%. We, as I have commented, we have also completed the first preparatory study under the current Eco-Design Directive. These are some results that we obtained by applying the methodology proposed in this directive. And you can see here, this is for the case of the fuel cell stack case study. You can see here how the global warming potential is decreased for each product concept, for the first two, the realistic one, and then we have the optimistic and disruptive. In the first case, that it is the realistic approach that can be reached in the next years, we have just a good decrease in this global warming potential. It's more or less 1/5 of the total global warming potential. But if we go for the life cycle costing also, we have also a good decrease in the total cost. In this case, you can see here that we obtain a good decrease in the realistic case, but for the midterm, that means it will be reached in the next 10 years, more or less. Then we have also this information about the criticality materials, and we are applying here the methodology proposed in the directive, and you can see how these new product concepts decrease the use of critical raw materials. And this is important because, you know, this is a key point for our hydrogen field, our hydrogen sector. And finally, in this preparatory study, we also benchmarked the performance of this fuel cell car against battery cars, and we saw that the fuel cells and hydrogen technologies are very competitive with the battery cars. It depends, okay, in the total system and definite total system. And one important thing that we found out is that the tool proposed in the Eco-Design Directive, the Eco-Report tool, has to be updated to be applied for the hydrogen products of hydrogen technologies. So about risks and challenges, okay, we need the involvement of key actors for the generation of ideas of these new product concepts. Actually, in this project, we have Symbio France, that is car manufacturer, and he has been checking all these guidelines. And also, we have a very good contribution from our external working group, our advisory group, that is composed of some of the main manufacturers of solid-state electrolyzer fuel cells, like Solidera, and also we have the support of the JRC in this project. Again, we are hoping that this guideline will have a very widespread use. So we are also preparing some dissemination events. I have commented in the C project that they will have a special event in the European Hydrogen Energy Conference to be held in Bilbao. So this will be a shared event between C and EGHOST, just to show first the guidelines for life cycle thinking approaches, and then we will see the application in eco-design. Just the next steps is just to issue the final sustainable by design guidelines for the both products, including the final assessment of both stacks with the guidelines from C. And also we are preparing guidebooks, the EGHOST guidebook, that will be a general sustainable by design guidelines to be applied for any fuel cell and hydrogen product. Coming to exploitation, we are following here the same approach for C. All our material will be in open access, will be in the public domain. So we are not looking for patents or any economic exploitation, but of course we will have the exploitation plan in May, just by the end of the project. And about the impact, with the gas line, we want to show that the sustainability is very important in the hydrogen sector, is a very important factor for decision making. And also with this line, we are looking at increasing the eco-efficiency and also the circularity of the hydrogen device. We have begun with solid oxide electrolyzer, with fuel cell, open fuel cell stack, but this methodology could be applied to any hydrogen products. So then we hope that this guideline and the EGHOST will be a good support for decision-making processes just in the design phase of these products. And that was all from my side. Thank you for your attention.
Thank you very much, Javier, and we fully agree that indeed the sustainability is very important for the hydrogen sector, as you mentioned in the end, and glad to see as well these two projects tackling very important activities, trying to bring all the three dimensions of the sustainability all together, the environmental part for the LCA, the economic LCC, the social as well, SLCA, into these specific guidelines and move further with the eco design. Very important activities in our view as well. Consider as well different challenges related to the variability of different parameters and even, I would say, the maturity of the technologies. I think that all technology, to get more solid information to allow, getting with a solid analysis, I think this still pose a kind of issues or challenges. One point that I would like, maybe the time is still with us, to get from your side, we learn from Best for High how important to have industrial players in the projects. And I was wondering now, if did you find as well what was the role of the end user partner? You mentioned about Symbio France in the validation of the guidelines. If you can share with us something very short.
Yeah, sure. Yeah, Symbio France has been a very valuable partner because he has contributed also with some inventory information for the C and for EGHOST. And as end user, they are just testing the guidelines for the life cycle thinking tools and also for eco-design guidelines. Actually, they are the coordinator of the work package of the task for issuing these eco-design guidelines, and then they are just facing the problems with the eco-design from this industrial perspective, because we are in the research part, so some things could be easy for the research part, but it's not so easy for the industrial side, and they are checking just these non-matching opinions in this, and we are just trying to give the most useful guideline for the industrial side also. So this is a very valuable contribution from the Symbio.
Absolutely, glad to hear that again. Thank you very much, Javier. Let's see if some further questions will come towards the end of this session. Anyway, before moving on, I would like to remind the audience to add the questions in Slido, so we may have some time to address them in the end. Now, moving on, I'm pleased to invite the next speaker, Gonzalo Ramajo. He's a senior manager at Monitor Deloitte. Gonzalo will present some preliminary study of a very important study conducted on behalf of the Clean Hydrogen GU about sustainable supply chain and industrialization of hydrogen technologies. This analysis aims somehow to identify the strengths, weaknesses, and to assess as well the competitiveness of hydrogen supply chain, with focus on 14 hydrogen technologies. But I'm going to stop here without disclosing too much from Gonzalo's presentation. Gonzalo, please go ahead. The floor is yours.
Thank you, Claudio. Thank you. Many thanks for your introduction. That I think that you almost said as almost everything that I have to say. But as Claudio has said, we are currently analyzing the supply chain status, the European supply chain status, in order to understand really well the resilience their circularity level, the recycling pathways that are currently using. So it's a really relevant study according to our understanding, and why specifically understanding the complete supply chain. No, one of the main points that we have seen at the beginning of our study, and I'm going to enter into details in a few seconds, is that it's extremely important to pay attention to the supply chain in the very early stages of the development of the supply chain. No, we had some experience in the past about the supply chain development for other clean technologies, like for example photovoltaic fuel cell, photovoltaic cells, photovoltaic inverters, and all these and all other equipments that are currently very relevant in the clean energy landscape. And as we maybe had some troubles with our supply chain with all these components, right now we have a not as good position as was in the past. No, so it's very relevant according to our understanding. Pay attention to the supply chain development at the very early stages of its development. Okay. So basically, what we have done, or what we are doing, because we are more or less at the 70% of the development of the study, okay, we are trying to describe the state of the art of the hydrogen supply chain in Europe. We identified the main strengths and gaps for the supply chains. We also in another stream, we are trying to make an inventory of all the European entities that are currently working on the supply chain status of the hydrogen supply chain status. So this is a very relevant also task. And we also want to understand if the current gaps, the current strengths, the current weakness, or the opportunities that we are seeing right now currently in the supply chain of all these technologies, how can evolve to the past, no? Because this is very relevant. We have seen that there are some weaknesses that can evolve in there are some weaknesses that are more relevant to others, and there are some weaknesses that the problem is that the supply chain needs to evolve because the technology needs to evolve, because as you can imagine, as we have seen in all other presentations, the technology is in a very early stage. So the supply chain that provides equipment and components to all the industrial manufacturers are in a very early stage also. No, so we need to understand the current gaps, the current opportunities, the current strengths, and how this can evolve in the future. No, according to some scenarios that we also have done for this study. No, and also very relevant part in this second stage is also understand the sustainability level, no, of the current supply chain. This is, the other presenters, I think, have described very well some initiatives regarding the sustainability. We have seen that this is a current problem more for the industrial manufacturers, not in the R&D stages, but more in the industrial phase, because currently, of course, manufacturers are working on reduce costs, try to fix their supply chain, try to be competitive with foreign providers. So the sustainability maybe is not his top priority at this moment, but of course it's something that is very relevant for everyone, and also for the European Commission, as has been already mentioned, is also a very relevant part. So okay, this is another relevant issue that we are currently analyzing. And the main goal of this study, finally, is to develop recommendations, policy measures, R&D activities, in order to promote the European leadership in the hydrogen technologies. No, so we need to, as I said at the beginning, no, at this very early stage of the development of the supply chain, we need to take smart movements as a continent in order to enhance, make more resilient our supply chain for this technology. This is also something very important, and we will provide some recommendations for that. Okay. So basically, we are analyzing 14 different technologies. Okay, of course, we map more than 50 technologies related with hydrogen, but I mean, we try to select the 14 more relevant, or the 14 more relevant, not in terms of hydrogen use, that also this was one of the main criteria, but also maybe technologies that need to develop a specific supply chain, no? Because there are other technologies that they have or they share supply chain with other more mature technologies, like for example oil and gas industry or natural gas industry. That is a much more mature industry, of course, and the supply chain is much more mature. So we try to select the 14 technologies that we believe that Europe needs to put more attention on their supply chain. No? Of course, the PEM electrolyzers, alkaline electrolyzers, SOEC and IM electrolyzers, and also waste to hydrogen gasification technology that also we believe that can be a good solution for the development of renewable or low carbon hydrogen. Okay. In the field of logistics, we are analyzing the ammonia cracking, the hydrogen storage tanks, also the hydrogen refueling stations that we believe that is also something very relevant. And finally, grid infrastructures. No, we will include pipelines and compressors, and this is something that also very relevant to us. No? And last, end use technologies, like for example fuel cells, PEM fuel cells, and solid oxide fuel cells. That I think that has been already said a lot in these two previous sessions. And also DRI method for steel decarbonization, hydrogen gas turbines, and synthetic methanol. So these are the 14 technologies that we are currently analyzing in depth. Okay. As we haven't finished the analysis, but I mean, as I said, we are on the 75% of the development of the study. We have some preliminary insights, preliminary findings. Please take carefully this information. But I mean, we believe that are some ideas that are really relevant. Okay. Well, I didn't say, but the main sources of information for all this study is basically we have done several interviews with supply chain stakeholders, producers, component producers, critical raw material producers, final manufacturers, some research institutions. So we have done more than 60 interviews, expert interviews along these months. So I mean, we have done a good expert. We have a good expert panel that is helping us with this insight, and also we analyze the literature that is currently available on this field. Okay, so basically some preliminary ideas. Okay, so we believe that one of the most relevant part, one of the most critical part, is to try to reduce the complexity of all these mechanisms, permitting requirements to become green hydrogen or to develop a green hydrogen project in Europe. Okay, so right now the main focus for a green hydrogen project developer maybe is not in Europe, maybe it's in other regions of the world, United States with the famous ERA. So currently, as the supply chain is developing, supply chain players are following the projects, and the projects are right now focused, or a little bit more focused, on other parts of the world. No, so and one of the main ideas here is the complexity in order to develop a green hydrogen project, for the mechanism structure, the grants, the requirements to become green. So it's a little bit more difficult than other parts of the world. Okay, so 2 and 3 are more or less linked. Basically, we have some strong dependencies on two main ideas: critical raw materials, especially for PEM electrolyzers, but also for other technologies, and also we have some dependencies from electronics, for example, and also for carbon fiber and glass fiber. This is three examples of some dependency. So we need to search for supply alternatives for these critical components, and also at the same time, and this is something that at the research level Europe is working with a lot of effort, is to reduce decrease the critical raw material dependence by developing new ways new materials, new ways to produce the hydrogen, and new ways to other ways to use other materials for the equipments, and that are able to reduce the critical raw material dependence that we are currently facing in some specific technologies. Okay, that is also a very relevant part. Okay. The fourth idea is that also Europe needs to increase the automatization and of the R&D, but especially of the manufacturing activities. No, also, we have analyzed that the current automatization production in some technologies is quite lower than in other parts of the world, especially, for example, if we speak about fuel cells compared with Asia players. We have a lower automatization rate in general terms than other parts of the world. So we need to increase the automatization, especially in manufacturing activities, in order to reduce cost and decrease time to market for components. Okay, so this is also very relevant part. The fifth idea is regarding circular product design. I have said at the beginning, maybe this is not top of mind for European suppliers, and this is something that need to be addressed, because currently there is, I will say, I don't know lack, but at least there is lower circularity design, lower recycling pathways at manufacturing, at industrial level, not in the research level. There is several projects working on that, but at the industrial level, the circular design and these recycling pathways maybe is in a lower stage of development that we should need. No, as I said at the beginning twice, the circularity product design or the recycling pathways for several components is not the first priority for industrial players. Okay, of course, it's maybe for some research projects, but at the industrial level they have another priorities, and we need to address at the same time this necessity to have a more circular supply chain, because it's necessary for Europe, and also to be competitive worldwide, because otherwise we can lack our we can lose our current position in the worldwide industry. Okay. Next idea, we need to decrease our time to market of different products. Okay, as a result of we need to decrease some regulation, automatization for as I said at the beginning. As many are research and development activities, like the quickness of to be able to be on time on the market. So we need to reduce this time to market of several products. This is something very relevant part. And finally, there is not currently a problem, because as I said at the beginning, this very early stage is not big enough in order to have a problem. But one of the main points can be attract expert profiles to the industry. One of the ideas could be increase the awareness of the hydrogen industry to attract more expert profiles to industry, because we believe that this is an industry that will require new profiles, and we need more. We could need in the future more experts in that field. So that's basically the preliminary findings that I can share with you. We are currently working on that. And well, that's basically all the information that we would like to share with you in this conference.
Thank you very much, Gonzalo, for some hints about this preliminary study, the results of this study. I know that there is a lot of effort behind to get all the information. I know that you are really conducting a very intensive campaign, trying to talk to the industry to get their views from the field. And we really believe that this is going to be the real added value of the study. The analysis is still ongoing. We are looking forward to finalize the study early next year. And indeed, we are believing that there will be more information to share, the final conclusion and the results of the study to be released somewhere in after the spring next year. So looking forward, and thank you very much for your insights. Thank you.
Thank you.
I think time is getting now a bit short. I think we can move further. As it has been announced actually yesterday by our director, the Clean Hydrogen Partnership will launch soon with the help of an external contractor, the European Hydrogen Sustainability and Circularity Panel. In this regard, I will invite Eszter Kantor, project manager at Ecorys, who will disclose a bit more information about the upcoming call for expression of interest for experts application and selection. Eszter, the floor is yours. We can see the presentation, and I think it's always
and now I have my voice back as well. Thank you so much for the introduction. Yes, my name is Eszter Kantor. I represent a company called Ecorys, and together with our partner TNO and our subcontractor Grant Thornton, we have been contracted by the Clean Hydrogen Partnership for this new initiative to set up and manage this new initiative called the European Hydrogen Sustainability and Circularity Panel. So I'm going to be introducing this new panel to you, and hopefully this works. Yes. So after the introduction, I'm just going to be briefly discussing the expression of interest, which is upcoming, and the structure and focus of the panel, and give you an example of the sample of activities, the activities that we can expect the panel to carry out. As mentioned, the panel is established on behalf of the Clean Hydrogen Partnership. It is composed of up to 15 experts who have knowledge and experience in sustainability and circularity issues linked to hydrogen-based technologies, their value chains, and other cross-cutting issues. The focus of activities will be twofold. On the one hand, they will be required to support the Clean Hydrogen Partnership at project and program level. Now, what does this mean? It basically focuses on sustainability and circularity aspects and ensure that these elements are sufficiently addressed and managed at both program and project level. There's also another element to the role of these experts, and that is communication and public outreach, the promotion and dissemination of knowledge, raising awareness about the sustainability and circularity principles, and how can they be better integrated into projects. The panel will be set up early next year and will remain active throughout the duration of 2024. We are currently working on an expression of interest, which will hopefully be launched in the next few weeks. So please watch out for that. We will be advertising this on our platforms, web-based platforms, as well as on our social media sites. The expected tasks I have already introduced, but I think it's also worth mentioning that experts, these 15 experts that will be active in the panel, will be will be in task forces. The task forces will be thematically structured, which we will be introducing in the upcoming slides. There's an expected resource input, which is basically the availability of the experts, which we foresee to be between 20 and 25 days for the next year. This can be, of course, distributed into days or half days, depending on the workload. These will be discussed when the panel is set up. We have designed an application system which is relatively lean and easy to manage. It is composed of a web-based application form. Annexes will include the declaration on honor and a CV. So it will it is very user-friendly. So hopefully it will generate a lot of interest. So this is the call that is you are expected to see pop up. Please look out for the hashtag EHSCP. The expertise required is not surprising. So at least 6 years of experience in the field of activity related to hydrogen technologies, circular economy field. Having experience in EU-funded projects or academic work on hydrogen is very advantageous and beneficial. Of course, sufficient availability from the experts and a high level of English knowledge, which is going to be the main language of communication. And here you can see the thematic areas which cover the entire supply chain, from raw materials to waste management, end uses, and eco-design as well. The sample of the activities, so what can we expect for this panel to tackle? It can include the definition of indicators, sustainability and circularity indicators in various thematic areas. It can also mean that they will be requested to evaluate projects in view of their sustainability and circularity, to look at, to provide suggestions, recommendations to the Clean Hydrogen Partnership on how to improve the possibility to highlight the sustainability and circularity aspects through the reporting templates and the methodologies that are being used, or their own program design. And as I've mentioned before, there will be opportunities for awareness raising and external communication within the project as well. We will be organizing workshops where the experts would participate, the panel experts would participate. And on the right side of the slide, you see the task force distribution, which aims to cover the supply chain, the entire supply chain. So this is the call, and this is the advertisement, so the outreach, the communication material that you are expected to see. There's we have designed a recognizable brand for this panel. The hashtags Clean Hydrogen Partnership and EHSCP will be used across the various platforms. So we are hoping that these will be, of course, accompanied by other communication activities, including webinars and other meetings, perhaps at events such as the EU's Hydrogen Week, which is taking place quite soon. So that's it. I tried to be brief. I hope to manage to keep in time. Thank you all for your attention.
Thank you, Eszter, for the presentation, and mostly for staying on time. Indeed, very much appreciated as we are approaching the end of this session. Thank you for supporting us in launching, in the preparation, and in the coordination of this panel. More to come in the near future about with more details about the call, the process, and this is kind of invitation to just to stay tuned, follow up on the information that will be released soon through other websites or other communication channels. Thank you very much again. We promised from the beginning to take some questions from the audience. We may be a few minutes late. We apologize for that, but I hope this will be fine for the speakers and audience. We have received few questions, especially on the first project for the best for high, for instance. Let me address quickly to you, Ilaria. It relates to the TRL of the technologies developed in your project. What is the TRL, and how the processes and the technologies developed in the projects can be brought out further at the industrial scale And if so, if this in the cost-effective way, and how long it would take to have these technologies at the largest scale. So there are a few questions in one, if you can just develop around them.
Yes, yes. Okay, so most of the technologies that we developed, we managed to get to TRL 5. So it's little scale, clearly. There is already a little engineering being done to ensure that there are, for example, the processes are continuous rather than batch. So this is a first approach that we had. The only technology that is still at TRL3 is the one about the recovery of lanthanum and cobalt. But all the other are TRL5, including the processes for the gas dismantling, so to separate very neatly the CCM from the membranes, and also the process for the manufacturing of the platinum ink, including the recovered platinum before putting it then into the new MEAs. How long will it take to get to the next phase, up to, I don't know, TRL 8, for example? Well, these are processes which really needs time. I mean, a rule of thumb is that you perhaps need at least a few years to get to such a large development, because we are talking about larger scale engineered, completely engineered processes. But I think that there is an issue here, which is about the actual volumes of the end-of-life materials that we are going to face. I don't know whether in 3 years, 4 years, we will have already the volumes of materials that need to be treated. But at the same time, it will be really, really good to be able to take these technologies up to a higher TRL for checking that actually we get the same yields. We managed to continue to obtain the same amount of recovered materials, and also to be able to deal with perhaps the difference in technologies that we see. Also, there is a need to perhaps try these technologies more widely on other types of hydrogen technologies. We already tried with the electrolyzers, and we have some very good results that we need clearly to keep working on and complete. And then perhaps we need to try on different technologies, and it would be really good if this type of recycling processes are suitable for a wide variety of technologies, because that would be a real strength. But until we try, we don't really know. So, and then I hope I finished the question.
Yeah, thank you very much.
Yeah.
I think it was very, very related. I mean, to the question. I was still wondering, what about the cost? Did you perform some techno-economic as well to check whether these new technologies are as well, let's say, cost-effective somehow, or is it too early to address that?
Well, we are looking into it. Clearly, again, the low scale, the lower scale of TRL doesn't help, but we are doing some scenarios analysis to understand if we were to obviously have higher volumes, to introduce some automation, etc. What could be the result? And for sure, there are the value of the materials that we recover, especially if we are talking about the precious material, makes it worthwhile. For the other materials, then there are other considerations that come into place. So, for example, for cobalt, the fact that we are actually sourcing it perhaps not so socially sustainably as we would like.
All clear. Thank you so much.
Thank you.
Let's see if there is another question, and I think there is one for Javier related to his work in the project. You show as well in your presentation you mentioned about the collaboration with the Joint Research Center, and I think the question relates to that as well, to the presentation given yesterday by the people from the Commission. which says that the GRC is currently preparing an LCA checklist for the fuel cells and hydrogen technologies. The question is to explain a bit what is the relation between the GRC checklist and the guidelines developed by your projects, and so how these two items are linked to each other. Javier.
Okay, thanks for the question. Both actions are totally aligned because we have been collaborating with the JRC experts on life cycle assessment, and actually they are supervising our guidelines and we are supervising the checklist. So then the idea is to have align both. Then you can fill the checklist with our guidelines. This is the final idea behind this. So both initiatives are totally aligned in this way.
Excellent. Thank you. I think there are no further questions, so this allows us to just take a little bit behind the schedule, the deadline. I would like to thank you, all the speakers and the audience, for the attention you paid over this 1 hour and a half. I think the session, and in terms of some takeaway from this discussion, I think we all agree that the sustainability, circularity, strategic autonomy, I think there are very important topics, not only for our partnership, but as well for the European Commission, but as well even further to the entire hydrogen community and other stakeholders. So far, our partnership, I believe, demonstrated a large commitment to address this challenge from different angles, from different projects or initiatives. And of course, I think we all agree that many activities are not only ongoing, but this will needs to be further implemented. I'm pretty sure that more results and achievements will come throughout the next year. This will be presented not only in the next hour program review days, but I think will be shared as well throughout the year through different channels, webinar or workshop. So I think this is all. Now it's going to be a short break, and other parallel session will resume at 11:30 with, I hope, other so interesting discussion. And this is an invitation for our audience to stay with us. Thank you, the speakers. Once again, have a nice day. Thank you.